Welcome. In this video, we will be discussing secant lines, tangent lines, and derivative, what that is, and how did mathematicians find it. So I will be running you through the sort of process that mathematicians use to find derivative. So we start with 2 points, a and b, that lie on some function. It really does not matter what function you'd use. I have here 0.1 times x squared plus 3, but really it doesn't matter. So we take these 2 points, a and b, and we draw a straight line going through them. And we call this a secant line. A secant line is the line that intersects a function at 2 different points. And to find the slope of this line, we would take the function at b, subtract by the function at a, and divide by the change in those two values, or b minus a. I'm sure most of you would realize that that is the formula for average rate of change. So we could say that slope of the secant line equals average rate of change. And we're actually going to give a new formula to average rate of change. It'll be a slight modification than this f of b minus f of a kind of formula. So we're going to say instead that average rate of change is instead equal to f of a plus h minus f of a over h. And what h essentially is the change between a and b. So f of a plus h is f of b. It's just a different way of writing it, because we find using the change between those two values to be actually much more useful. So h is the change from a to b, so b minus a, or just some change in x, right? Because these are two x values that we're using here. So we take this secant line and we ask the question, what would happen to this line if the value b were to get closer and closer to a? So essentially what we're asking is, what is the limit as b approaches a? So we take this value and we just inch it closer and closer until eventually b is so close that we can't properly give it a quantifiable amount. This still isn't even close representing how close b can get. Because we basically say that b and a end up being infinitely close together. So we say that the distance between them is what we call an infinitesimal. This dx is an infinitesimal. And this is notation that is very common in calculus. It's very fundamental to almost every concept you use in calculus. So what dx basically is this infinitely small change in x. Because b can never truly get to a, because if it does, if b ever equals a, we have an undefined function of the tangent line or some kind of line here, right? So b gets infinitely close to a. And we end up is what I just said, a tangent line, a line that intersects the function at essentially one point. Because b and a are so close together, they basically function as one point, even though they are infinitely close to almost being, but they're not quite. So let's focus on the slope of this function. So we know that with linear functions that the point at every point of the slope of every point of the function is the same. So the slope here is the same as the slope here, which would be the same as the slope at this point. So we can basically say that the slope of this function, this tangent line, is the slope of this function at this point and this point alone. Because again, this is the only point where the function and tangent line merge, where they intersect. But how do we find this slope? Because we can't use this average rate of change formula. It wouldn't work with this infinitely small change in value. So we basically realize that as b approaches a, the distance between the two approaches 0. Again, never actually gets there because then we'd have an undefined function of the tangent line. But h can approach 0. So as the secant line approaches this tangent line, we can say that the slope of the secant line approaches this kind of slope of the tangent line. And we find that by taking the limit as h approaches 0. Because again, as b gets closer and closer to a, that secant line gets closer and closer to a tangent line, and the distance between b and a gets closer and closer towards 0. So we can say that the slope of this tangent line is the slope of the secant line as the distance between the 2 points a and b gets closer and closer to 0. So the slope of the tangent line is what we call an instantaneous rate of change. Instantaneous rate of change. And we also define this as a derivative. What a derivative is the slope of a tangent line. So what we end up doing is we end up taking this idea of a tangent line and applying it to every point of the function. So look at this kind of graph I have here. We realize that we can do this for every point of the function. And we ask the question, is there any relationship between the slope of all these lines? And if there is there a kind of function we can assign the slope of these tangent lines? And it turns out it is. These slopes are all related and we can define it with a function. But that is something I will cover in a later video. So that was secant lines, tangent lines, and derivatives. I hope this video helped understand some pretty confusing topics in calculus, but it's all so interesting and fascinating that I think it's really worth putting effort to and really trying to grasp. So thanks for watching. See you in the next video.